Hi, in this video we are going to take a deep dive into one of the most seminal papers regarding the diffusion models, which if you have heard about things such as DALL-E or any sort of painting application that takes, for example, text or some other thing and generates very realistic and beautiful images that are semantically meaningful to a human person, you probably have indirectly been introduced to diffusion models. So this paper is called Denoising Diffusion Probabilistic Models. This work has been done by UC Berkeley, and the general idea is that you take an image and you try to add small amounts of noise to it in a step-by-step process, and you want to basically have a model that is able to iteratively denoise a completely noisified image. For example, you take, let's say, basically a tensor the same size of the image, but with all the pixels, let's say, randomly sampled from a Gaussian distribution, and you pass it to this model, for example, 1,000 times, and you want to obtain a picture which is going to be meaningful to a person. Now, what that means is that considering that there is a probability distribution over, for example, the space of images in ImageNet, or, for example, the distribution corresponding to realistic images, what you want to do is to generatively model that, meaning that you want to interact with that probability distribution and in a parameterized fashion model it. And modeling a distribution in a parameterized fashion in that case would be giving you the ability to sample images from this data. As further information regarding the generative models, it's noteworthy that they are especially also important in the healthcare domain. When you have applications for which data, especially supervised data, are less available, it would be beneficial to be able to generate synthetic data that are going to make you able to train several models without having to, wait for, let's say some private data sets to be anonymized and then released publicly, and like signing 200 forms and things like that. So having a generative model has a lot of advantages, and that is one, for example, that have been used in learning with noisy labels, that have been used in many cases. And generally, there have been the three domains of VAEs, variational autoencoders. There have been the generative adversarial networks with the min-max game that they used to play, and currently the diffusion-based models. And they, like the connections between the non-equilibrium thermodynamics and deep learning has been first investigated, I believe, in a paper in ICLR 2015. And this paper here is also building on top of that. And so the diffusion models are pretty important these days. In the example here, you can see that the images generated by the generative modelings of images in the deep learning have been pretty successful, as the images are semantically very meaningful. So let's talk about briefly what the overview of this paper is about. So you have, denoising diffusion probabilistic models. And the idea is that you have something resembling a Markov chain like this, and let's say xt is going to be a sampled pure noise data and x0 be a semantically nice image. You will have something like this that you want to get from xt to x0, this sequence of random variables that you can see here, x0 to xt, so x1 to xt. So this is going to comprise your diffusion model, and x0, for example, would be a semantically nice image, and xt again would be a noise from a prior distribution. Now, this paper is about discussing the reverse process and the forward process of it. It's going to discuss the connection between this and denoising score matching, and also with the non-equilibrium thermodynamics. It's going to show that there's going to be some equivalence in there, and it's going to discuss from certain information theoretical perspectives how a diffusion model is actually good. Let's start from the abstract. The paper first starts by talking about its goal, which is high-quality image synthesis, and quality in this case means basically the image being semantically adequate so that when you look at it, you feel like it's a real image. And the way it is done is via generative modeling of this distribution. It does have a focus on non-equilibrium thermodynamics and its connection with the deep learning, and it's going to show a novel connection between the diffusion probabilistic models or diffusion models and denoising score matching, with the Langevin dynamics. They do certain information theoretical analysis and show that their model could basically resemble a progressive lossy decompression scheme, and it could be interpreted as a generalization of autoregressive decoding. Their code is also available in this URL. And one thing to note from the start is that their method results in high quality images being actually generated. So from the qualitative standpoint, it's known that it's a good model. First, let's talk about the definition for the concept of diffusion models or diffusion probabilistic models. Per the paper, a diffusion probabilistic model, which they call diffusion model for brevity, is a parameterized Markov chain trained using variational inference to produce samples matching the data after finite time. Okay, so now we know the definition of the diffusion models. The idea is that you want to reverse a diffusion process, and basically you are dealing with a Markov chain that gradually adds noise to the data in the opposite direction of sampling until the signal is destroyed. In other words, you want to reverse this information destruction process. One thing to note here is that this assumption of gradual addition of noise and the fact that you can now basically add it as small amounts of Gaussian noise, it is sufficient to set the sampling chain transitions to conditional Gaussians too, as is said in the paper, allowing for a particularly simple neural network parameterization. So having this Gaussian conditional assumption is going to enable you to efficiently parameterize your neural network models and utilize it in this process. And diffusion models are straightforward to define and efficient to train, which makes a good case for the use of them in generative modeling of images. And this paper is going to show that even though there have not been a demonstration that they are capable of generating high quality samples, that it is possible to make use of them in order to do that. Another important thing that they mention is that, let's read this part, we show that a certain parameterization of diffusion models, which basically the thing that they have here, is going to reveal an equivalence with denoising score matching over multiple noise levels during training. This is like one equivalence that they show. And the other one is with the annealed Langevin dynamics. This comes back to the non-equilibrium thermodynamics. I believe this model is mainly for modeling like molecules, etc. But they basically want to show that diffusion models have this type of equivalence with this concept as well. And basically they focus on these equivalences and demonstrating those as their primary contribution in this domain. Okay, there are certain important points in here. One, you know that the sample qualities, the generated images, are semantically nice because you can see them as a human. You can see that basically the images that are generated using these diffusion models are great. Now, this means that from the qualitative standpoint, they're good. Now, their models do not have competitive log likelihoods compared to the likelihood-based models. So that means that in terms of a certain quantitative measure, their models are not competitive, but at the same time, there are high-quality images generated by them. Now, one thing that they have found out with this regard is that let's read this part. We find that the majority of our models' lossless code lengths are consumed to describe imperceptible image details, which reminds you of what? Yes, compression. And then they presented a more refined analysis of this phenomenon in the language of lossy compression. They show that the sampling procedure of the diffusion model is a type of progressive decoding that resembles autoregressive decoding along a bit ordering that vastly generalizes what is normally possible with autoregressive models. So this part of information theoretical analysis of this, also from the perspective of rate distortion, shows that basically diffusion models are good. One important thing to note in here regarding the DDPM is that it is trained using variational bounds. So when you read the paper, you encounter that they mention that we use the usual variational bound, and that is ELBO, or evidence lower bound. Let's go over the overview of that as a background information to see what exactly it is and what does it mean, and then let's go back to the paper. So with regards to ELBO, consider the generative modeling concept. You have X, which is a random variable, which corresponds to your observation. For example, X could be the random variable of your image, the tensor of the image, for example. And Z would be a latent variable which is unobserved. For example, the CNN representations, or like a label or something like that. So you have X and you have Z. You assume that X and Z are assumed to be basically jointly distributed. In other words, you assume that there is a connection between them, otherwise, the whole thing would be not exactly meaningful. Your goal in general in generative modeling of this concept is to approximate, learn, and interact with the distribution, the true distribution that these observations actually come from. So you assume that there is this P star of X that you don't know about. And the idea is that in a parameterized fashion, you want to introduce basically a model to basically try to optimize it from a family of models to resemble the P star. So when you're trying to estimate this probability distribution, the idea is that you consider a family of models. For example, let's say theta is the weight set for, let's say, resident 50 or something like that. You want to assume that there is a value from this set of values from this model family that can be found, for example, by a sort of optimization that models the joint distribution of x and z, or the observation and its corresponding latent. So you have, when you define this sort of generative model, you have access to the p theta of x and z. Now, the thing that is important is that you want to eventually deal with this marginal, meaning that you want to interact with a modeled version of the true distribution over the space of these observations. For example, the distribution of images. So you can sample from it, interact with it. Now, if you look at this, given that you have this p theta here, this marginal is going to correspond to this, meaning that you look at the joint distribution. By the way, this is a definition, but it's also true. So if you take p theta of x and z, you can basically integrate over the values of latent and obtain this marginalized distribution p theta x. Usually it is not something that is tractable to 2 because you have a lot of choices for the z here. Again, the goal of p theta is to often present a nice log likelihood for the observed data. So this is one way to measure how good this distribution, this parameterized distribution is for the model. And the way it is that you want it to obtain, a good log likelihood value, meaning assigning high probability to the observed value. Now let's see what the ELBO wants to say. The idea is that if you sample any data point from this distribution that you model, let's say an image, if you look at the log likelihood of the image, for example, p theta of x, which is the marginalized result over there, that's going to show you the likelihood of the p theta of x, and then you have basically the logarithm of that. By the way, the p theta of x basically is the likelihood that you have observed example x, the probability of observing example x given theta, which is the likelihood of theta over x. That's essentially the thing that you are centering your attention around. So the idea for the ELBO is that this value that you're trying to maximize is lower bounded by this variational bound, and often focusing on optimizing this is easier. So let's see what this is. The bound says that if you consider a Q, another parameterized distribution, parameterized by the parameter set phi, which parameterizes the probability distribution of z, the latent random variable, given x. So if you have a parameterized model Q like this, and you sample z's and take the expected value over these instantiated z's, and internally you have this value over there, you have basically this lower bound over there. So on the top you have the joint distribution of x and latent, and at the bottom you have the Q of z. So this log likelihood over there is going to be the evidence for x, and this term over there is going to be the evidence lower bound for x. Assume that the p star is the true distribution. What you want to do is that you want to parameterize and choose a model family, let's say p theta of x, and you want to model that. So what ideally you want to do is that, first of all, you want to define some sort of loss function that measures the similarity of this probability distribution that you have introduced with the original true probability distribution. And how do you want to measure this? So assuming that you have L, you want to keep sampling random samples from this true probability distribution, and you want to take the expected value of this. This results in a loss that in general measures to what extent this probability distribution models the true distribution, and you want to pick the theta in a way that this sort of divergence is minimized. I didn't specifically use the word distance here, but the idea is generally you want to make these as similar as possible. Thus, it means that we want to consider implicitly parameterized probability distributions. What does that mean? Consider the PZ, which is going to be a distribution for the latent. For example, it could be a Gaussian distribution. and then define f theta. It could be, for example, a convolutional neural network or something like that, and use it to model the p theta of x and z. Now you sample z from this prior distribution, for example, Gaussian, and then now with that, you parameterize the p theta of x given this latent distribution. So for sampling, you first pick a z, and then you put it inside this, you deal with this conditional probability and you sample x from it. Now, how do we construct this one? Note that you are going to deal with this marginal over there. So you would want to compute this function over here, which is impossible to compute again for the aforementioned reason of having a lot of latents to go over. So let's see what do we need to do. So when we want to model the p theta of x, you can write it like this, using the Bayes rule. Introduce the latent z, condition the x on z times probability of z. What this gives you is the probability of x and z. In the bottom, you have the probability of z given x, which is probability of z and x, which will be simplified with the 1 in the denominator. It's also divided by the probability of x, so it goes up, and theoretically these two are equal. This is the written version of that. So you can see that you open this up, you cancel these two, again z and z, and then bring the p of x to the denominator, and you will have this. Now we need to approximate this. So having z, you have this probability, and this basically is what your model gives you. This p of z is going to be a prior, so both of these are easy to compute. So we gotta have to figure out a way to deal with this one. In order to deal with that, and in order to make the problem tractable, we introduced Q, which is another parameterized model, which is going to, in a discriminative fashion, because you have z condition on x, rather than dealing with the joint distribution, which would say generative modeling, which is what we were doing prior to this. This parameterized discriminative model is going to focus on the probability distribution of latent given observations. So this is going to model that and make the problem tractable. Let's go over it again. So you have the prior over latent. For example, it would be a Gaussian distribution or something like that, a multidimensional Gaussian distribution, independent, etc. Then you have the probability distribution of x, the observation, given the latent z, which is something that is easy to compute given that you have parameterized a model to deal with that. Now, x is the random variable corresponding to your observation. Let's say x is observed. You have the p theta of x given z. This is going to give you the likelihood of the latent. So you have latent z, you have the observed x. This is going to, this is going to be the, so if you look at the p theta of z given x, what this gives you is the posterior probability, meaning that if you have a prior probability of a z being the latent value, assuming that you have x conditioning on you having x, this is going to give you the posterior probability. And as you may know, posterior probability equals, so you can use the Bayes rule, write it this way. What this means is that if you look at the posterior probability, it's going to be a result of a prior times the probability distribution of x given z, which is the likelihood of the latent z, or the likelihood basically to what extent z is describing the process of x. So what this also might remind you of is things such as the Bayesian logistic regressions, or any cases in which the prior information takes a role. So yeah, this is basically what you have over there. And then you want to say that, okay, I have p theta of z and x. I want to model it in this parameterized fashion with q of phi. One thing to note here is that this is basically a proportion. It's not exactly identical. Okay, so we want to approximate this like this. So we need to do this because otherwise we have to compute like p theta of z and x. And what this means is that you would need p of x, which is computed this way, which is impossible. So let's write this again. You want to parameterize p theta of z and x. How can we write this? We can write this as this. Since you write it as this, you would need this denominator value, which is hard to compute. So that's the motivation for q. So you want to find a good approximation for that using the q parameterized with the parameter set phi and z conditioned on x. So this is also called amortized inference. Okay, let's write it differently then. So looking at the p theta of z and conditioned on x, you can write it like this. So pz is easy to compute, p of x given z is also easy to compute. You want to deal with this one. So you model this one with the q. All right, let's proceed. You have the expected value. Okay, so you basically have this expected value that you want to maximize. And you want to figure out what exactly is the relationship over there. So if you consider this observations being sampled from the true distribution, and you're looking at this, you know you can plug in this P star as multiplication and division over there. Then you can open it up like this using the logarithm rules and calculus. Okay, so on the left side, you will have this thing over there. I'm sorry, it's actually the reverse of this order. So this one is going to be ln of P star. So you would bring the P star into it because you're taking the expected value and then integrate over it. This is going to give you the negation of the entropy of the true distribution. It's not something that is under your control. You can kind of ignore it. Then on this part of the deal, you can actually have another negation sign and bring the P star over there to the top and make it a KL divergence. Let's see how that would work. So as you can see now, you have the KL divergence between the target true distribution and the reference, the thing that you're optimizing, the P theta of x. Meaning that you can basically write it like this. So you can see that focusing on this log likelihood and focusing on this KL divergence is kind of equal to each other. So trying to maximize this is trying to essentially minimize that. So the goal is to obtain a theta which maximizes this kind of like a energy function or the negation of a loss function. And the way to do is that you sample a lot of examples from the true distribution. For example, you take a lot of images, and then you compute this ln p theta of xi divided by 8. So basically, you get this empirical expected value, and you try to sort of assume that this is the same as this. And then you focus on this probability t. You use the Monte Carlo integration, and basically focus on e of the expected value of z being sampled from this latent and this conditional over there, which is P theta of x and z, Q of z and x. So you basically are focusing on the variational bound over there. One thing to note is that looking at this, you can see that this thing over here is going to be an unbiased estimator of P theta. Now note that the logarithm function is nonlinear, so you cannot directly go from this to that. And one thing it means is that if you take an example from the x, from the P star, if you take the logarithm of ln P theta of x, it'll be equal to the ln of this x, this expected value over here. So again, you have x and z with the parameterized of z and x. So you have this equation over here. So you want to use the convexity of the logarithm function and see what exactly it would get you to. Note that the logarithm function is concave, so if you look at this curve, it's going to be something like this. For example, take 2 points. If you take the function logarithm, the value of the function applied over the, let's say, the x-axis value of the average of these two, which is here, the value of this function is going to be larger than this. So this goes back to Jensen's inequality, and you can write it like this. So given that you have the logarithm of average, for example, it'll be function applied on this. This is going to be lower bounded by the version of this in which you have brought this one out. So it'll be larger than equal to this expectation over there. So thus you end up with the ELBO, which was this. Going back to the concept of diffusion models, you have this sort of a Markov chain over there. And the probability distribution over the x0, this is going to be essentially the thing that you're trying to model, meaning that x0 is your semantically meaningful image. You want to use theta parameterization in order to have a probability distribution P that models this. You're trying to model the true distribution so you can interact with it. You know that it's basically a marginalized version over there. Note that this additional noise addition is going to give you that x1 until xt are your latent unobserved random variables. So this marginalization essentially equals to this. So you can assume that in our previous discussion, z over here is x1 to xt. This thing over there is called the reverse process, which is the joint probability distribution over x0 all the way until xt. So x0 again is your image, and x1 to xt are all of latents of the same dimensionality as x. And you assume that there is a true distribution that images are being sampled from. Thus, you're focusing on the generative modeling of that using diffusion models. Okay, so p theta of x0 and t is the reverse process. So it is a Markov chain of basically Gaussian distributions, the learned Gaussian transitions, in order to denoise basically the noisified image into a meaningful one. What that means is that let's say you sample xt from a distribution, a well-defined distribution, for example, Gaussian, independent Gaussian distributions, 0 and I. 0 being the average, I being the covariance matrix. You define the p theta of x0 and t, or in other words, the reverse process, like this. So what this means are multiple things. So one thing is that looking at this, you can see that this is basically equivalence of a Markov assumption, a Markovian assumption. So you have this independence sort of going from t to 0, for example, for t minus 1, from, let's say, t plus 1, and so on. So read it like this. You sample you sample xt from this prior distribution, and then you keep doing this transition, going from xt to xt minus 1. Now, in order to model the xt minus 1 with xt, they use the Gaussian transitionals. So this is read like this. You have a parameterized model that models the probability of going from t to t minus 1, or denoising. What this means is that if you look at this, which gives you the value of the probability of observing xt minus 1, a value for xt minus 1, given that you have observed a value for xt, given the parameters at theta, it is modeled as a Gaussian distribution, in which you plug in this xt minus value and get your result, which is parameterized by a mu theta, using xt and t. Note that it's independent from the t plus 1, etc. And you have the covariance metrics, again, parameterized like that. And you have the forward process, which is focused on q. And you have it like this, going from 1 to t. You are noisifying essentially the image. So this transition is defined again with another Gaussian conditional. So when you have xt minus 1, what this basically says is that you take xt minus 1, you scale it by this parameter. By the way, beta going from 1 to all the way to the last step t, which is usually 1000. This is called the variance schedule. What you have here is that you use this as a multiplier of the I. So you're sort of independently adjusting values with this variance. And then here you are scaling the average over there. So you basically are adding Gaussian noise in additive iterative steps to your previously observed observations. This over there, again, remember the Q of z and x, or the Q of latent given observation. This is the approximate posterior over there. Note that you have Q of latent given observation. This is called the posterior of latent. It is fixed to the Markov chain of gradually adding Gaussian noise as shown above. And again, beta 1 to beta t is called the variance schedule. Now let's look at the variational bound, or ELBO, for this. So you have the logarithm of the likelihood over there, and this is going to be the upper bound on this loss. And you can open this up and write it like this. And note that in this type of expansion, you now have this probability of xt separated from these transitionals that describe the forward and reverse process. Now, with that loss, you need to define the variance schedule, or beta t's, which are hyperparameters that can either be fixed or be learnable parameters. And then parameterizing the Gaussian conditionals for the reverse process. In their notation, you have 1 minus beta t being the alpha t, and alpha bar t would be the multiplication of all the alphas before. The advantage of that is that in the forward process, now you can have a closed form and sample xt, t not necessarily being just one increment of the previous index, and just go from x0 directly to xt. And it will be basically, so the probability of having a noisified xt given an observed x0, for example, an image, would be the Gaussian with the x0 being scaled with square root of alpha bar t, and this factor by multiplying the identity matrix as the covariance. The reason why that's the case is that if you consider two Gaussians, for for example, mu1 and sigma1 being the average and covariance of the first normal distribution, and the two index is basically the second one. If you define another random variable as a summation of x and y, the distribution corresponding to that would be a normal distribution with the summation of their averages and summation of their covariance matrices. Now let's look at x0 to x2. This is not the same notation as the x0 before. This is just showing how exactly this scaling process would do. So let's say you have an x0 sampled from a normal distribution with the average of 0 and the covariance matrix of I. X1, let's say x1 is defined this way, meaning that it is sampled from this normal distribution with x0 being scaled by square root of 1 minus beta 1 and the covariance of beta 1I. You can write it as this, so essentially you can write it as this, basically the baseline, plus this other random variable which is sampled from average of 0 and the covariance matrix. You can do the same with the x2 and expand it, and you will get to this based on x0 by substituting what we found for x1 in the position of x1. Now you can see that with this multiplication you essentially have the square root of alpha 1 times the square root of alpha 2, so this will be the square root of the alpha bar 2. And as you can see that the square root was missing over there, but yeah, that would be what it would be. And then you have two normal distributions, one with this covariance, the other one with this. So you can essentially sum them up. And by doing so, you can basically see that you will have 1 minus alpha 2 times alpha 1, or in other words, 1 minus alpha bar 2. And this essentially could be served as some sort of an induction step, and it would show the closed form that you saw before. Again, what this means is that you can pick an arbitrary time step t and basically get the qxt condition on x0 like that. Now let's go back to the original variational objective, which was this. And this is the thing that we want to focus on optimizing. We showed that it could be opened up and written like this. And this could be further extended and written like this. So you have the logarithm of this. So P, or the probability, the reverse probability that xt is sampled from is a known prior, so you can have it like that. And then you have these transitionals, and you have sort of the initial transitionals over there. So you have basically the three separate terms. Now let's look at this. How else can we write the q of xt given xt minus 1? So it was shown in the paper in ICLR 2015 that you need to introduce the x0 to make this tractable. And given the Markov assumption, you can essentially add the x0 over there. And then you can use the base rule to write it like this. So you have q of xt minus 1 given xt and x0, q of xt and x0, q of xt minus 1 given x0. So we know the closed forms for these two. So we also need to kind of put a major focus on this one. So let's combine. By writing the q of xt minus 1 given xt like this, you have this new formulation, which will be simplified like this. As you can see, this q of x1 and x0 has kind of been removed. And on the left side also you have this additional q of xt given x0. If you look at it more closely, the first one, you can essentially take this negative sign and kind of like move this on the top. You will get the KL divergence between this reference distribution, which is the q of xt given x0, with the prior you had on xt. On this part, you will have the KL divergence between this transitional and these distribution. So again, you have like a summation of certain KL divergence terms. And the last one would be this term. Another derivation which is not tractable but is theoretically interesting is like this. So you again use the Bayesian rule, but you do not introduce the x0, and it can be written like this. Essentially, it will boil down to the KL divergence between the q of xt and p of xt, And then here you would have the average of all of these KL divergences between this, basically the corresponding transitionals. And eventually for this one, because you have the ln of q of x0 and you're getting the expected value over this EQ, you will have the entropy of x0 over there. In their notations, they refer to the first one, which is the forward distribution on xt given x0, KL divergence of it with the p of xt. They refer to it as LT with the uppercase T. For each one of these terms inside this summation, you have LT minus 1, which corresponds to the KL divergence between the q of xt minus 1 given xt and x0. We'll talk about this more. And the p theta of xt minus 1 given xt for the reverse process. And then for the L0, you will have the p theta of x0 given x1. Now here's an important derivation. So we want to show that if you look at this q of xt minus 1 given xt and x, by the way, this is x0, that you will have it as a normal distribution with a average and basically a factor for the covariance scale. Now this mu for this time step t, the mu tilde, is a function of xt, which was one of the conditions, and x0 the other one of the conditions, and can be written like this. So it's kind of like a complicated formulation. And then you have the covariance one, the beta tilde t, being this scaled version of beta t. Now let's see why this is the case. First of all, you cannot remove x0 or xt, because if you look at the probabilistic graphical model of this, you are interested in xt minus 1, and the variables that you observe are xt and x0. So the presence of each one of them does not make xt1 independent from the other one. So both of them play a role here. So in order to compute that, you use the Bayes rule and basically write it like this, meaning that you take xt on the other side. You can kind of ignore the x0. x0 will be the condition. So if you, for example, define another renamed distribution of xt minus 1 given xt, it would be essentially the Bayes rule for that. So keep the x0 in the conditions, use the Bayes rule on this to, you bring the xt on the other side. So you have the q of xt given xt minus 1 and x0. And you multiply it by the q of xt minus 1, so you can have the joint distribution on the top, and then on the bottom you will have the q of xt condition on x0. So if you, for example, ignore the x0 for now, it'll be like q of the probability of xt condition on xt minus 1. Now we know the closed form versions of this, and therefore one other thing we know is that when we look at the q of xt given xt minus 1 and x0, it will essentially be the xt given xt minus 1 because of the Markov assumption. And it's going to be proportional to this exponent over there. So you have this average based on the rule, because you are looking at the transitional xt given xt minus 1 in the forward process. So you have this scaled version of xt minus 1 serving as your average, and you will have this beta t to kind of serve as your scale for the covariance. Now again, when you look at this, you can write it as a Bayes rule like this. Note that we remove the x0 from this one due to the Markov assumption. So you have this term, and we can sort of combine them and see what exactly would be the corresponding statistics for the Gaussian that results from this. So you have the x. From the first one, you have this term, then the second one, and the third one. You will expand it, and it becomes something like this, and let's add the last term as well. So it becomes something like this. Just nothing complicated going on over here, so you just essentially expand this one, which becomes this, expand this becomes this, and expand this one, which becomes this term. Note that you can rewrite the above like this. So you will have this factor being, for example, a constant multiplying by xt minus 1 squared. You have minus 2 times this factor over here times xt minus 1 plus some other terms that are not a function of xt minus 1. So you do not see xt minus 1 appear over there. So you can see that assuming that it's going to be something like a xt minus 1 minus a mu to the power of 2, you will have to be able to find it by dividing this whole term by 2, meaning losing this factor and then dividing this by this. So if you do that, you will have this term and this term. So this term will be here, this term would be here. And you can simplify it like this. So this is kind of Again, if you want to write this something like this, xt minus 1 minus mu into 2. So in the bottom here, you will have this term. So alpha t plus beta t would be 1. Alpha t times alpha bar t minus 1 becomes alpha bar t. So you can simplify it and write it like that. And add the other term to make it like that. So you have basically the mu tilde of t shown. As for beta, you basically want the inverse of the factor that multiplies the xt minus 1 squared, which is the inverse of this term, which can be written like this. Since this paper is going to focus on a concept called sufficient statistic, I just felt like it would be good to just go over what exactly sufficient statistic meant as some sort of background information first. So assume that theta is a parameter that you're trying to estimate. For example, let's say that the average height of a population or something like that. And x be the basically a random variable corresponding to your observation. For example, you could have n sampled heights of this population, for example, and that would basically be an instantiation of this random variable. Now, tx, or a function of this random sample, that gives you a value. Any function of this random sample is a statistic. Now let's see, what does sufficient statistic mean? Consider this equation over here. So on the left, you see f of x, so basically the probability distribution condition on the sufficient statistics value for the random sample. So what this basically means is that, let's say x is an instantiation of this random sample. For example, let's say n is 100, and x could be, for example, the height of the first person is 80, the second person is 90, something like that. And these values actually don't mean much, but yeah. So let's assume the first one is like, I don't know, 150 centimeters, the other one is like 180 centimeters, things like that. And then t is a value, for example, for the statistic that you're considering, and theta is the parameter that you're trying to estimate the value for that. So you know that you can basically open this up and write it like this. So on the bottom, you're going to have the probability of t given theta, and on the top you have x. So basically you don't touch theta and you use the Bayes rule for this. One thing to note is that given that t is a function of x, assuming that you have x, you have t, so you don't need to like write f of x and t. That one will be vanishing from here. So roughly it could boil down to something like this. It will be the probability parameterized by theta, the thing that you're trying to estimate. For example, a Bernoulli distribution, a Gaussian distribution, something like that. And then on the top, you have the probability values for essentially obtaining the instantiated sample of this random variable of your random samples. So for example, the probability that the 100 randomly sampled people that you have measured their heights correspond to exponential xn. And then on the bottom is basically the theta. For example, let's say you have the statistic that you're considering be mean, and let's say it's the probability for that average to be, for example, 160 centimeters or something like that. Now, when do we call tx a sufficient statistic? The condition for that, and it's a definition, so you don't necessarily have to prove it, but you can kind of intuitively see what this is about. Tx is a sufficient statistic if you consider this probability, meaning that having tx, you're considering the probability of x. You know that there's a theta here. If this probability does not depend on theta, meaning that if it is a function of only x and t, then you can say that t of x is a sufficient statistic. One thing it means is that you're considering your random samples, and then intuitively tx is basically the thing that you need in order to estimate the parameter theta. The point here is that t of x is sufficient if it contains all of the information that you need in order to estimate theta, meaning that you cannot do better of a job at estimating theta if I give you the entire values for the random samples. That kind of means that there's no branch in this probabilistic graphical model from x to theta. And one other thing this conditional here means is that when you have the value for this t, these two become separate in this probabilistic graphical model, and therefore you will have this conditional assuming that tx is sufficient statistic. Again, this g of xt means that you're no longer dependent on theta. One other thing that I mentioned is that when you have two Gaussians that you're comparing and you're computing, for example, K divergence or cross entropy or something, you don't necessarily need to do the expensive Monte Carlo estimation. You can use closed form formulas. For example, if you look at two Gaussians, Qx and Px, parameterized by this mu and sigma, and if you want the cross entropy between them, which is this formula over there, you don't need the Monte Carlo estimation. You can derive it like this. You can write the formula for Px, and when you expand it, it becomes this. So the point is, if you have something like this, the computations will become simpler. You do not need to necessarily do Monte Carlo estimations. The first thing we need to choose is the variance schedule, or the beta t's, over here. You also need to define the model architecture and parameterize Gaussian distributions for the reverse process. They also showed an explicit connection between diffusion models and the denoising score matching. One important thing here is that they do not learn the betas here, and they focus on adding small Gaussian noise through a large number of steps. So in defining the forward process variance schedule beta t, instead of making it learnable, they fix them to constants. And therefore, because these betas are fixed to constants, this posterior q is not going to have any learnable parameters. Therefore, the LT, when you have on top, remember that PFXT is something like a Gaussian distributions independently sampling each one of the dimensions. So this LT here is not going to have any sort of term that you can optimize over. So this can be constant and removed from the loss function. As for the reverse process, which is supposed to do the denoising, so you have the p theta of xt minus 1 given xt. It will be basically parameterized as a Gaussian with normal distribution of xt minus 1. You have mu theta and you have sigma theta, parameterized with xt and t. Let's see what the design choices made in this paper are. So you know that for the sigma of xtt, they chose to make it basically having the scale times the covariance matrix identity. And they experimented with this sigma t2 be beta t and another option to be the beta tilde of t. And the results they showed that were similar. The choices for the seed were being sampled from the Gaussian distribution of 0 and I. And they also tried the fixed point. They kind of were playing with the lower bound and upper bounds of the reverse process entropy. Now, another important question is the parameterization of the mu theta of xt and t in this reverse process. Again, remember, you want to reverse this diffusion process. Thus, you need this to parameterize the p theta of xt minus 1 xt, which plays the important role of reversing this diffusion process. Note that this p theta of xt minus 1 xt had a major role in lt minus 1 in the definition of the loss we defined based on the ELBO bound. And that loss could be written as something like this, given the fact that you are looking at KL divergence of Gaussian. So again, you do not need to do the Monte Carlo sampling once you have the information regarding the parameterization of the average and standard deviations. So this term is not going to be dependent on theta, the parameters of the model that you're trying to optimize, so you can ignore this one and focus on this. Note that when you're looking at this reverse process, you basically want to go from xt to xt minus 1. So let's write xt based on x0. So you know that this based on this closed form formula, you can essentially, if you have x0, you know that the average is going to be like this. So you can separate this and write it as this baseline plus this error term. So let's say you sample epsilon randomly from a Gaussian distribution of 0 and I. You could scale it by 1 minus alpha bar t and add it to this. Therefore, you will have x0 written as xt like this. Now let's come back here in the paper. Here you have lt minus 1 minus c, so you removed c here and you're focusing on only the parts of lt minus 1 that depends on the theta on which you're trying to optimize. And you will have this term over here. And here you would have the xt like this. You know that the mu tilde of t was parameterized based on xt and x0, so you can kind of, write it like this. And this would be purely writing mu t based on xt, in which xt itself is a function of x0 and this error term. Now note that you want mu to essentially minimize this loss, so you want basically this to optimize this. Okay, so you now have the mu theta. Based on the formulation we just showed, it's going to predict this term over here given xt. Okay. Now, this means that you can parameterize mu theta to be something like this. So here what this means is that everything is essentially the same. You just have this parameterization of this error here, which is a function approximator that's supposed to predict the epsilon or that error from xt. Now let's read this part. To sample xt minus 1, what you do is that you take the xt minus 1 from this. This is what you want to do. What you do is that you compute the xt minus 1 based on this formulation in which z is sampled from the Gaussian distribution with 0 and I, and epsilon theta is the parameterized version that's going to basically predict epsilon from xt and the time step t. Now, the other important thing that they do is showing the connection between this and the Langevin dynamics, which is in the sampling the algorithm 2. The Langevin dynamics, which is, I believe, a model that is proposed for modeling molecules, what you have is that you have a forward process in which you have this term here, which is the gradient of the logarithm of the distribution over there, and then you have these additional terms. They show the connection between this dynamics and this sampling formulation over here, and basically showing that this epsilon theta, the parameterization, is supposed to learn the kind of like a parameterized estimator of the gradient of the logarithm of the distribution. Now, one other thing to do is that if you go back to this LT minus 1 definition, let's say you want to kind of bypass this mu tilde over there and write everything based on epsilon, you will have this simplified formulation of LT minus 1, which brings you down to this. Note that now you have this epsilon minus parameterized version of epsilon theta. Now this formulation resembles denoising score matching over multiple noisy scales indexed by t. Thus, they show that we see that optimizing an objective resembling denoising score matching is equivalent to using variational inference to fit the finite time marginal of a sampling chain resembling Langevin dynamics. And they've shown that the epsilon prediction parameterization both resembles Langevin dynamics and also simplifies the diffusion model's variational bound to an objective that resembles the denoising score matching. So they showed the connection to one to the Langevin dynamics and non-equilibrium thermodynamics in deep learning, and the other one is the denoising score matching. So equivalence between showing this type of diffusion model with these two. For the reverse process, they consider the image data essentially as u into 8, so the values are between 0 and 255. They scale it linearly to -1 and 1. And then to obtain discrete log likelihoods, because you want to predict something like this, they consider the last term of the reverse process to be an independent discrete decoder derived from this specific Gaussian over here. Now, if you look at this formulation, what this basically means is something like this. You have a Gaussian distribution with certain mean and average. Any x that you pick, given the fact that you have basically mapped it to -1 and +1, you consider a width of 2 divided by 255, 2 being 1 minus 1 minus 1. And you consider this surface to be the probability you associate with that x. There are two boundary cases, of course. One, if x is 1, in which instead of the 2 by 255, you consider the past 1 per 255 width plus everything that comes after, and d minus 1. Coming back here, they mentioned that this choice here ensures that the variational bound is a lossless code length of discrete data without need of adding noise to data or incorporating the Jacobian of scaling operation into the log likelihood. One thing that they have found is that the sample quality, it was beneficial for the sample quality to focus on this simpler to implement thing, which is the simplified version of the loss that focused on epsilon and epsilon theta. And yeah. One thing to note is that in this expectation, t is uniform between 1 and t is usually 1000. One thing that is important about this is that there was a weight over there which was discarded. So this simplified objective discards the weighing that it had before. So it's itself a weighted variational bound that emphasizes different aspects of reconstruction compared to the standard variational bound. So it's not necessarily optimizing the same thing, therefore it's okay to see two different results. And what happens in here is that the diffusion process that they have causes a simplified objective, which is shown here, to downweigh the loss terms that correspond to small t. Now, why is it good for the sample quality? Is that they conjecture that, okay, so these terms train the network to denoise data with very small amounts of noise. So when you have t being small, means that the amount of noise that you have to reconstruct is very small. So it is beneficial to downweight them compared to when you have like more difficult tasks and noisier things and larger values for t. As for their experiments, again, they set t or the number of steps of 1000 to all the experiments. They choose these values for beta 1 to beta t, scale them linearly from 10 minus 4 to 0.02. They make sure that the signal to noise ratio at the xt is as small as possible. So if you look at the KL divergence of this Q, meaning that having x0 when you reach the last information at the last stage, when you have the xt, you kind of want to make sure that all the information is sort of lost. So if you look at this prior distribution or P of xt, this KL divergence between these two is very small, and that shows that most of the information is kind of lost in that diffusion. And therefore, it will teach the network to interact with the probability distribution rather than memorizing things. They use a unit backbone and train the model with that. With regards to the reverse process parameterization and training objective ablations, there are three important findings. One is that when you chose to predict the mu tilde instead of the E or epsilon, it was the baseline option. So if you focus on this, it works well only when trained under true variational bound instead of the unweighted mean squared error. Second was that learning reverse process variance by incorporating a parameterized diagonal sigma theta into the variational bound led to unstable training and poorer sample quality. So they figured out that choosing a fixed variance schedule is better. And three, predicting epsilon as proposed performs approximately as well as predicting the mu tilde when trained on a variational bound with fixed variances, but much better when trained with a simplified objective. They also focus from the progressive coding perspective as well. And there are multiple interesting things. So first of all, if you look at the code lengths of the Cypher 10 models, so the gap between train and test is going to be very small, which means that the model is not overfitting, given that this gap is small. So that's one thing to note. One, they mentioned that their lossless code lengths are better than large estimates reported for energy-based models and score matching using annealed importance samplings. They mentioned that they are not competitive with the other types of likelihood-based generative models. Now, having that, plus the fact that their samples are of high quality, they conjecture that, okay, diffusion models have an inductive bias that makes them excellent lossy compressors. From the rate distortion theory analysis, they focus on these terms, or these plots over here. And with the algorithm strain 4 that they mentioned, they discussed that this distortion decreases steeply in low rate regions of the rate distortion plot, indicating that the majority of beats are indeed allocated to imperceptible distortions. After that, they also focus on progressive generation. So, for example, look at the figures here, such as this one. They mentioned that we predict the results of the reverse process x0 while sampling from the reverse process using algorithm 2. So you can see when you go from the image to this one and going back to this, as you go forward, so for example, when you get to this part, the large context of it, for example, that I don't know if it's a bird or something, the main object is still somehow apparent, but then most of the information gets lost as you go forward. They also show the connection to the autoregressive decoding. For that, they have a specific formulation. For example, they consider the setting the diffusion process length t to the dimensionality of data, and then they consider the forward process so that xt given x0 places all probability mass on x0 with the first t coordinates masked out and masks the tth coordinate. So this is specific formulation that they discuss here. Kind of shows that in a reformulation version of the diffusion model, training the p-theta with this particular diffusion is kind of training an autoregressive model. Lastly, they also mentioned that you can interpolate source images. So for example, if you take x0 and x0 prime 2 images, you can have Q as a stochastic decoder and interpolate these two in the latent space, meaning that you get the code of them or kind of like bring them back to the sample, to xt, using the forward process of xt given x0, and then you can linearly interpolate them and reconstruct them using the reverse process to reverse the diffusion process with correspondingly interpolated latent and get the result. And that concludes the discussion on the DDPM paper. Now let's look at some of the generated images using this type of diffusion model. This, for example, is an image of the interpolation